Alrighty, we're going to move on to problem 13, which is asking us about this reaction underneath here, about right-handed 2-bromobutane being converted to 2-butanol, and it takes place in conditions A and B. So first we want to identify those conditions. Both cases we end up with the same thing, looks like. They both end up there, but of course it's going to be slightly different depending on the mechanism. So first we'll talk about A. We have a strong nucleophile in that O negative, and obviously in both these cases we're using substitution because we started with the bromine, we ended with something else, you substituted it. So this, because we have a strong nucleophile, this should tell us that we're looking at an SN2 reaction. Over here we have water, which is a really weak nucleophile. Ergo here we're looking at SN1. So let's look at the mechanisms in between these two. Both cases you start off, of course, with that bromine. The main difference is SN2, also known as backdoor attack. You have that O negative hitting the opposite side of it and making it escape in one step. So here we have the bromine and the OH leave and arrive at the same time, resulting in the final compound shown above with that alcohol up there. And this, of course, is one step. And if we did it with our water, we actually have to do an SN1. In SN1s, the bromine must leave first. So the leaving group leaves. You have this intermediate that can do other stuff too, hydrides and carbo or methyl shift, sorry. And then finally water decides to come around and take that positive charge. And then another step, because we still have that H in deprotonation, when one of these H's decide to leave and hang out with another water molecule. Actually, this would look like the electron stays there, and then another water that's just hanging around takes that H, and you're stuck with, cleaning up a little bit, the product here. Of course, we should know the main differences between these, and that's what we're going to be asked about. So this table was on the answer sheet, and it's asking us, first off, is the new alcohol chiral or achiral? They're the same thing, so we know that they're both going to be either one or the other, and since we're looking at these, we know that they're both chiral because they're attached to 4 different groups. So we're going to check off yes on both. Now, is the alcohol optically active? Yes or no? Okay, so this, we need to know whether they're R, S, or racemic, or / a mix of both. And for that, we have to know SN1 versus SN2 mechanisms. In SN1, because we have this intermediate here, that has no say whether it wants to be R or S, so we're going to end up with a racemic mixture, as opposed to up here, when we have that backdoor attack, when it takes that spot of the BR, it pushes it away and pushes a new group in that spot, and it takes a new spot and flips inverts its optical pureness. So at first it was R, so it's going to end up being S, but we know it's going to only be S because it can only work by that mechanism. So is it optically active? In the SN2 case, we know that yes, it's going to be optically active. Here in SN1, we're going to end up with racemic. So let me put an X there, because it can't decide whether it's R or S. It's going to give you a mix of both. And here we have configuration of alcohol R and S. We already said that SN2 is a backdoor attack, so it switches it. And here it's asking us both. Of course, it's going to be both, as we discussed. Now we want to know whether these are an inversion, racemic, or retention of configuration. Retention's if it stayed the same. Since we flipped it, we actually would be an inversion here. Simple definition, just flipping it. And the other one, our other option is retention or racemic. Obviously this gives us racemic. Alright, our last question. If the concentrations of the reactants are doubled, how does the rate change? 8 times, 6 times, 4 times, or does it double? For these, we need to know the rate law for these guys. You can have them memorized. Good way to remember is this is dependent on two things and this is dependent on one thing. So this is two reactants. This is the concentration of the nucleophile. This is going to be SN2. And multiplied by the halogen group, your carbon halogen group. And SN1, you have that constant again, but this time it's only dependent on that R and X. That's because the rate determining step is this leaving. You don't need the halogen or the nucleophile, sorry, to facilitate that like above. In this case, this pushes it away, and here it just leaves by itself, and that's the step that takes the longest. So here you're dependent on two because you have to; these two things have to collide in order for the reaction to happen, and that's your rate determining step. Here you just gotta wait until that halogen decides that it thinks it's more stable on its own. So if we double the concentrations, we put this 2, 2, 2 of everything, we'd end up with, if we multiplied those across, we'd end up with 4K. And then those two original concentrations, I'll just put, I'll label as nuc and Rx. Let me try to clean up a little. K, concentration of Rx, and concentration of your nucleophile. So now we know that this one's 4 times when you have this, and the new one, SN1, you only had a 2 in front of that. So if we reconfigure that, we have 2 times the concentration original. These concentrations are constant in both cases, so we know that we just have that new 2 in front. And that's just from multiplying these guys together and rearranging. Okay. The key step here, the way I remember, is since I don't remember these rate laws on their own, I just know that SN2 takes a collision between two molecules, and I know what those two things are, nucleophile and Rx. SN1, I know the rate determining step is the halogen leaving, and that only is dependent on one thing.